Welcome back to the Deep Dive. Today, we are strapping ourselves in for quite an intensive look at something the sources are calling the industry's top trending certification.
Yeah, we're diving deep into the Mancha Certified Autonomous Systems and Cloud Engineer Certification, MCSCE. Yeah,
MCSCG. And it really does signal a fundamental shift in what technical expertise means today, doesn't it?
it really does. We're not just looking at, another coding boot camp here. This is more like analyzing the blueprint for the kind of tech professional we'll need tomorrow.
So this deep dive, it's all about that unique integration this certification seems to capture, combining autonomous systems, cloud computing, engineering expertise.
That's exactly it. The
Yeah.
ability to seamlessly merge robotics, these intelligent AI agents we hear so much about, and then the scalable global backbone of cloud deployment. That's the magic mix.
Absolutely. So our mission today is really to distill the technical blueprints, the career paths, which look pretty elite, based on the material all coming from the Mancha Virtual Institute of Technologies, or MVIT. So if you, listening, want a shortcut to understanding how you move from maybe being a really skilled software developer now to becoming a certified expert who's ready to, well, lead innovation in fields like smart manufacturing, autonomous vehicles, designing intelligent automation, this is probably for you.
And the MVIT roadmap we've been digging into, it's pretty compelling. They don't just give you the curriculum list. They lay out the specific technical prerequisites, the detailed learning modules, and maybe most importantly for you listening, the explicit financial prospects,
Wow.
what mastering the specific blend of engineering expertise actually translates to.
Because it addresses a critical shortage, doesn't it? The lack of engineers who can, not just build the autonomous system, but also deploy it, manage it at enterprise scale in the cloud.
Exactly. That deployment piece is key.
Okay, let's start right at that core definition then.
Yeah.
MCSE Mancha, Certified Autonomous Systems in Cloud Engineer. I mean, the title alone tells you this is about engineering solutions that have to work in a pretty demanding, interconnected world.
That's spot on. The core idea, the mandate really, is creating intelligent, cloud-connected solutions. And the sources are very specific that this expertise is directly aimed at high-growth industries.
Like?
Well, think autonomous vehicles, right? The perception, the navigation models, they live on the car itself, but they're constantly talking back to a cloud platform for updates, data analysis, coordination. Or think smart manufacturing. You've got robotic arms on the factory floor, maybe being coordinated and optimized by AI agents that are actually running on a cloud infrastructure somewhere else.
So it's about building both the, let's say, the operational brain and the scalable infrastructure needed for this machine age.
Precisely. Both pieces.
And this isn't something you just, pick up over a weekend course. The sources lay out a pretty comprehensive 24-month duration. 2 years. That's a serious commitment.
It is intensive, yeah. And I think that's intentional. But the structure, right from the start, integrates real-world demands. That 24-month program, it includes 1 month of mandatory on-job training.
Oh, interesting. So immediate application.
Yeah, immediate application phase, exactly. And that's followed by a pretty rigorous 2-month final project, a capstone.
Okay, tell us more about that capstone. What does a candidate actually have to do to prove they're ready to lead these kinds of autonomous system deployments?
Right, so the capstone, it's the final proving ground. The source material says it pushes candidates to deliver a full end-to-end development and deployment solution.
End-to-end meaning?
Meaning they have to build the AI agent, or maybe the core autonomous function itself, design the secure APIs to control it, implement the user interface for monitoring it, and then deploy the entire stack, front-end, back-end database all into a cloud environment.
Wow.
Yeah, the requirement is basically that the graduate can operate as a production-ready enterprise developer from day one, not just someone who knows the theory.
Okay, that level of real-world expectation, it leads us straight to the institution itself, MVIT, the Mancha Virtual Institute of Technologies. You mentioned they operate on this kind of dual focus model, blending education with actual commercial development.
Exactly. MVIT sits right at that crucial intersection between what industry needs now and academic rigor. They aren't just an educational body. They have an operational software division that delivers complex enterprise solutions.
So they're actually building stuff for clients.
They are. And this hands-on, industry-driven specialization in commercial tech, it informs every single course in the MCSE curriculum.
Right. So when they're teaching what their own developers were probably using yesterday, not what some textbook recommended 5 years ago. How does that corporate specialty, directly influence the MCA syllabus?
Well, the sources really highlight that as the secret sauce, you
Yeah.
could say. MVIT specializes heavily in web and mobile apps, which clearly explains why that full stack foundation M1 is mandatory.
Uh-huh.
And critically, they specialize in cloud native solutions and API development. This means the MCSE curriculum has this unique bias towards low latency, scalable deployment. Their developers know that an autonomous system's value is basically zero if its data can't be processed in near real time on a robust, secure backend.
Makes sense. And what about their AI and machine learning focus? How does that feed into the certification?
Their corporate AML expertise is pretty broad, actually. Covers predictive analytics, computer vision, natural language processing. But what's most relevant for the MCSE is their specialization in automation systems.
Okay.
This anchors the curriculum in practical AI. So when you learn computer vision in, say, Module 4, you're learning the techniques that MVIT's own enterprise software division uses to enable, for example, quality control robotics on an assembly line or environmental perception for autonomous vehicles. It's grounded.
So the education is aggressively career-focused because the people teaching it are literally operating in the fields they're teaching.
Exactly. The certification programs are designed by these industry practitioners, and the goal is, frankly, uncompromising. Graduates must be job-ready with in-demand skills immediately, which mandates hands-on, production-level projects, industry mentorship, and a real focus on continuous learning, which, let's face it, is non-negotiable in the rapidly evolving world of autonomous systems engineering. You have to keep learning.
Okay, so let's say a learner commits to this. They go through the rigorous 24-month journey. The potential payoff looks pretty significant. The MSCIE is structured into 6 specialization modules, M1 through M6, and each one maps directly to a high-value career path in this autonomous and cloud engineering space. Let's maybe detail these 6 paths.
Yeah, this modular structure is really key to understanding the certification's versatility. It's designed to prove the graduate can handle the full life cycle of an autonomous project, from concept to deployment and maintenance.
Okay, so the foundational module, M1, that gets you the title Full Stack Software Engineer. Makes sense as a starting point.
Right. Then M2 quickly transitions into data, making you a data science analyst. Then M3 is that critical deployment phase. The machine learning systems engineer, that's a hot one right now.
MLOps, right. We hear that term a lot.
Exactly. MLOps is huge. Then you hit the higher strategic and research roles. M4 is the really cutting-edge deep learning research engineer.
Okay.
M5 is that crucial strategic leadership role, the AI solutions architect. And finally, M6 handles the deployment at, global scale, the cloud AI infrastructure engineer.
So 6 distinct but connected roles. And we have the data, the critical data from the sources to back up the value here. The financial prospects confirm the market demand is, well, pretty extreme.
It really is. The numbers are compelling.
Let's talk about these roles and maybe what they actually do, focusing a bit on the pay differences. It seems like there's a distinction between technical depth and strategic design. Which roles command the highest salaries?
Well, the deep learning research engineer, the M4 specialist, is highly valued for pure technical depth. They're looking at an annual salary range of $120,000 to $180,000. Yeah, and strong freelance rates too, $80 to $120 an hour. The sources note they tend to dominate AI startups and R&D departments. These are the people actually designing the next-gen neural networks for autonomous decision-making, the deep science part.
That makes intuitive sense. Usually, the deepest, most complex coding commands high pay. But according to the sources, the highest potential top-end salary actually belongs to the AI solutions architect, the M5 role. Why would strategic design be valued even higher, potentially, than pure research coding?
That's a really crucial question, and the answer, pulled from the source material, reflects what the enterprise market really needs right now. The AI solutions architect has the highest ceiling, potentially $130,000 up to $200,000 annually.
$200,000.
Yeah, and the most lucrative freelance rates, $100 to $150 an hour. The sources basically show the market pays a premium for those people who can bridge the gap between M4's deep research and the overall business objective.
So the deep learning researcher builds the amazing engine, maybe, but the solutions architect draws the blueprint for the entire factory using that engine. something like that.
That's a great analogy, exactly. The architect designs the entire system. They're choosing the cloud vendor, defining the ethical safeguards, ensuring data governance, guaranteeing the solution aligns with, massive organizational goals.
So it's broader.
It requires deep technical knowledge, absolutely, plus system design skills, communication skills, strategic planning. Those are the skills that lead directly to leadership pathways like CTO or VP roles.
Okay, let's drill down a bit more into the functional roles. What's the data science analyst M2 doing in the context of autonomous systems compared to the machine learning systems engineer M3?
Right, so the M2 data science analyst is really the foundational analyst. They're responsible for collecting, cleaning, validating the huge data sets generated by autonomous systems. LiDAR scans, sensor telemetry, diagnostic reports. They use tools like Python and Pandas for predictive modeling to find patterns, like predicting when an autonomous component might be about to fail. Their role is about generating insight.
Got it, insight. And then M3 shifts into operationalizing those insights.
Absolutely. The M3 machine learning systems engineer, earning a strong $100K to $150, is noted as having critical demand because they are the MLOps professionals.
MLOps again?
MLOps machine learning operations. It's the bridge between the data scientist who finds the insight and the production environment where it has to work reliably. They make sure the model doesn't just suddenly fail in production because the real-world data looks different or because it can't handle the scale.
So, if an autonomous vehicle's object recognition model was trained on sunny days but performs poorly in fog.
Exactly. The MLOps engineer is responsible for rapidly updating and deploying a new scalable model, maybe using tools like Docker and scikit-learn to handle the fog. They make these complex automation systems reliable.
That distinction feels incredibly important. I mean, reliability in autonomous systems is literally the difference between success and, well, catastrophic failure.
It is the absolute definition of making autonomous systems truly operational and scalable. And then finally, just to complete the picture, M6, the cloud AI infrastructure engineer, they're the specialist who manages the fleet, essentially. They ensure the data pipelines from the autonomous agent, maybe a car or drone, back to the cloud, AWS, Azure, or GCP, are super high speed, secure, and robust enough to handle the sheer volume of data that, say, 100 or 1,000 self-driving vehicles might generate simultaneously.
Okay. And the final key takeaway here seems to be the global nature of these skills. Is this expertise something that kind of locks you into the U.S. job market, or are these skills truly globally recognized?
That's a crucial question, and the source materials are really clear on this.
Yeah.
These cloud and AI infrastructure skills, universally required. The MKCE pathways lead to global opportunities because the core competency is full-stack development, building distributed cloud systems, MLOps. They're transferable across US, EU, and APAC markets.
So if you can manage a cloud-based robotics fleet in Detroit,
You can manage one in Munich or Tokyo. The underlying principles and technologies are the same. It's a global skill set.
all right, let's shift gears now and look at the technical starting line. This whole 24-month journey kicks off with Module 1, M1, Full Stack Software Engineer. Why is basic full stack mastery considered the fundamental starting point for something as advanced as autonomous systems engineering?
Because autonomous systems fundamentally aren't isolated bits of hardware anymore. They're connected, they're managed, they're monitored by software interfaces. So the M1 module is this comprehensive foundation that ensures graduates are truly enterprise-ready developers. They need to be able to build the control panels, the secure APIs for data exchange, the cloud backends for configuration and updates. It's a hefty 12-course module designed purely to provide that production-ready baseline. Without M1, you simply can't build the scalable interface needed to interact with your fancy AI agent later on.
Okay. So what exactly are they mastering on the front end side in M1 that's relevant to, say, building robotic control interfaces or monitoring dashboards?
The curriculum focuses on modern, industry-standard tools built for rapid iteration. They start with the absolute non-negotiable HTML fundamentals, the building blocks.
Okay.
Then they move pretty quickly into Tailwind CSS. Now, why Tailwind? The sources emphasize its utility-first approach because rapid prototyping and immediate UI deployment are just mandatory when you're iterating quickly on autonomous system interfaces. Time to market is often everything. You need to be able to rapidly change what an engineer sees on a diagnostic dashboard without rewriting massive, complex style sheets.
Makes sense. Faster changes. And the interactive part, React programming.
Yes, mastering modern React development using hooks and components. Then the leap to full stack integration comes through mastering Next.js. That's the big full-stack React framework, coupled with Vercel deployment for handling actual production environments.
So you learn deployment right away, too.
Right. This combination teaches the learner how to deploy a complete, scalable, functional application in a modern cloud context from early on. And of course, there's the necessary introduction to Python programming basics in M1 as well. That's the foundational language for pretty much the entire rest of the AI and ML curriculum from M2 onwards.
Okay, now here's where M1 starts to really justify the autonomous systems part of the certification name. The immediate dive into AI agent development, even before getting to the dedicated AI modules like M2.
Yeah, that AI agent focus is immediate and very application-driven. The M1 syllabus includes a specific course on AI agent development with N8N. Yeah, N8N is a really crucial tool for visual workflow automation and AI agent creation. It lets the learner immediately connect the full-stack interface they just learned to build to complex back-end automation processes visually.
So they aren't just like calling simple APIs. They're actually building complex automation pipelines right in M1.
Exactly. And they go deeper still with building agents with OpenAI SDK. That's pretty much the current industry standard for developing intelligent agents using modern large language model APIs. This really fast-tracks the AI application from day one. You're not just building a secure website in M1, you're building an interface that might configure, monitor, or even directly control an intelligent entity or a whole robotic fleet.
Okay, that definitely requires some rock-solid back-end fundamentals then. What are those supporting development and data technologies covered in M1 to make that possible?
It really requires three core things, according to the syllabus. First, API design and development, specifically focused on creating secure, reliable, RESTful APIs. These APIs are the communication tunnels, right, between the front-end dashboard, the cloud server, and potentially the autonomous system itself out in the field.
Ah,
Second, they need secure authentication systems. Best practices in security authorization absolutely critical when you're talking about remotely accessing potentially high-value or safety-critical systems.
look at that.
No way. And third, structured query language, SQL for database design, and robust data management. You need to ensure all that sensor telemetry, all those logs are stored efficiently and can be retrieved quickly for analysis or debugging.
You mentioned earlier that M1 is designed to connect back to core computer science fundamentals. Specifically, the sources highlighted object-oriented programming concepts, encapsulation, inheritance, polymorphism. Why are those particular concepts so essential when you're building large, complex autonomous systems?
Ugh. This is a point of significant depth in the sources, actually. These principles aren't just academic fluff, they are absolutely vital for system reliability and, crucially, maintainability in complex systems.
How so? Let's take encapsulation.
Okay, encapsulation. It's critical for separating and securing different system components. Think about a really complex autonomous system like a self-driving car. You absolutely want to encapsulate the logic for the braking system completely away from the logic for the navigation system.
Right.
Because if an engineer is updating the navigation code, you definitely don't want them to accidentally introduce a bug that affects the braking code. Encapsulation prevents that kind of dangerous interference.
Okay, so it helps prevent chaos when multiple engineers are working on huge, complex code bases. Makes sense. What about inheritance?
Inheritance is all about code reuse and extension. If you define a base class for, say, wheeled robotic platform, then all the derived systems, maybe delivery drone, an autonomous street sweeper, a warehouse cart, they can all inherit the basic movement functions.
Ah, so you don't have to reinvent the wheel, literally.
Exactly. Saves vast amounts of development time, ensures consistency across the fleet. And polymorphism, the third one, allows different components to respond differently to the same command, which simplifies the overall command structure. Imagine telling different types of robots to perform task. Polymorphism lets each robot interpret that based on its specific capabilities. These OOP concepts are mandatory for writing the kind of complex yet maintainable code needed to manage a massive fleet of robots or AI agents reliably over time.
And since M6, way down the line, specializes in cloud deployment, networking is another non-negotiable foundation taught early on, right? The sources even mention the OSI 7-layer model.
Yeah.
Why is understanding something seemingly theoretical like the OSI model crucial for someone designing autonomous systems?
Because it provides the essential foundational context for scalable deployment. You have to understand the different layers of communication involved. The sources highlight the importance of the basic client-server model, just defining how the agent's interface, the client, talks to the cloud brain, the server. But understanding the OSI 7-layer model ensures candidates grasp the lower-level mechanics needed to troubleshoot and optimize network communication effectively. When things go wrong, you need to know where to look.
Can you give us an example? Like, where does one of those specific OSI layers become really critical in the world of autonomous systems?
Sure, let's take the transport layer, layer 4. This layer handles things like error recovery and flow control. Now, imagine you are remotely updating the critical firmware on a robotic platform out in the field.
Okay, sounds important.
Extremely. You need that transport layer, usually TCP, to ensure the data packets containing that firmware arrive without corruption. If the data that dictates the robot's safety parameters gets garbled mid-transit because of network noise, you could have a critical failure, a catastrophic one.
Right.
So the cloud AI infrastructure engineer, the M6 specialist, absolutely must understand how TCP/IP guarantees reliability at layer 4 in order to deploy systems that are both fast and safe. Without that deep understanding, true scalability and reliability are basically impossible.
Okay, so we've established that solid M1 foundation, full stack, scalable, grounded in core engineering principles. Now we get to move into the really advanced modules, M2 through M6. This is where the full promise of the MCSEE certification, that mastery over autonomous systems and cloud engineering, is really delivered. Let's chart this progression, maybe starting with data and moving into advanced learning.
Right. M2 and M3 really form the analytical and operational core for the AI side. M2, the data science analyst module, focuses heavily on taking all that raw sensor data we talked about and turning it into meaningful predictive models.
So moving beyond just storing the data.
Exactly. They move beyond basic programming into proper statistical analysis, data visualization techniques, and predictive modeling using powerful libraries like Python and Pandas. This gives them the rigorous analytical mindset needed to truly understand the inputs and outputs of complex autonomous processes, what's really happening.
And then M3, the machine learning systems engineer, immediately focuses on MLOps and productionization, you said.
Yes, M3 takes those models developed or analyzed in M2 and makes them ready for the real world. The absolute focus is on productionization model deployment, building scalable systems using frameworks like TensorFlow and PyTorch. And critically, they master containerization tools like Docker.
Docker, explain why that's so key here.
Think of Docker as creating a perfect, tiny, repeatable environment for the machine learning model. If a model works perfectly in the M3 engineer's controlled virtual machine, Docker essentially guarantees it will perform identically when it's deployed onto a cloud server, or maybe even right onto the edge device of an autonomous system itself.
So it removes the "it worked on my machine" problem.
Precisely. It guarantees consistency and scalability and minimizes those deployment headaches when you're trying to manage hundreds, maybe thousands, of deployed models across a fleet.
Got it. Okay, next up, M4 and M5. These seem to define the highest levels of innovation and strategic design, research and architecture.
Yeah, M4, the Deep Learning Research Engineer module, is really the cutting edge. This is where they dive deep into complex neural networks. They focus heavily on computer vision, which is absolutely fundamental for autonomous perception systems.
How the machine sees.
Exactly. How it sees the world, detecting pedestrians, reading traffic signs, mapping environments using camera feeds, LiDAR data, radar, sensor fusion, all of that. They also cover natural language processing, NLP, which is critical for human-agent interaction, understanding commands, or even complex decision-making based on text input or reports.
And then M5, the AI solutions architect, moves from designing the specific model, like in M4, to designing the entire system blueprint.
That's the perfect way to put it. M5 focuses purely on enterprise AI solutions, large-scale system design, and robust cloud architecture. These are the strategic visionaries. They ensure the autonomous system isn't just technologically brilliant, but also secure, compliant, cost-effective, and ethical when it's scaled globally.
So they need skills covering everything from maybe NLP integration for customer service bots, all the way to ensuring AI ethics are built into the design from the ground up, not just tacked on later.
Exactly. It's a very broad, very strategic role, not just an afterthought.
And finally, M6, the cloud AI infrastructure engineer, the ultimate deployment specialist, you call them.
Yeah. M6 specializes in building and managing the complex distributed systems necessary for running these high-demand AI workloads. Managing data ingress and egress from potentially thousands of remote autonomous devices efficiently and reliably. This module covers the big cloud platforms AWS, Azure, GCP, ensuring the graduate can choose and optimize the specific cloud environment that provides the highest performance and scalability for, say, a multinational autonomous trucking fleet or a network of delivery drones.
Okay, now connecting all this advanced stuff back to the core promise, autonomous systems and robotics, there's that foundational prerequisite we need to talk about, the BASR syllabus, Basics of Autonomous Systems and Robotics. This is required just for the admission test, right?
Yes, the BASR syllabus is absolutely non-negotiable. The whole point of MESS is to create engineers who bridge software and hardware, the physical world, so you must demonstrate core engineering and robotics knowledge even to get admitted to the program.
So it's a filter right at the gate.
A crucial one. The BASR ensures readiness by covering specific fundamental robotics concepts that, frankly, are often ignored in pure software engineering degrees.
Okay, let's provide some detail on those key robotics concepts covered in BASR, starting with, I guess, the complex math involved.
Right. They include robotic kinematics. This is the mathematical framework for describing the motion of a robot arm, or maybe a mobile robot, without considering the forces that cause the motion. It's essential for figuring out, where the robot's joints need to be angled to reach a specific point in 3D space. Then they absolutely have to master sensors and perception. This details crucial technologies like LiDAR, light detection and ranging, for 3D mapping cameras for visual processing, and IMUs, inertial measurement units, for tracking orientation and acceleration,
How the robot senses its world and itself.
and the control mechanisms, how it acts on that information.
That brings us to control systems. Specifically, the BISR requires mastering PID controllers, that's proportional integral derivative and understanding feedback loops.
PID controllers, in simple terms.
In simple terms, a PID controller is what allows a machine like a drone trying to hover to maintain a desired state accurately, even with disturbances, like a strong crosswind. It constantly measures the error, how far off it is, and calculates a correction based on the current error, proportional, the accumulated past error, integral, and the predicted future error, derivative.
Yeah.
It's the absolute core of reliable, stable autonomy.
Got it. Stable control. And finally, path planning. Right. They cover path planning algorithms, specifically mentioning ASR, and RRT, rapidly exploring random tree, how the robot figures out how to get from point A to point B without hitting things.
Okay, that sounds like a real deep dive moment itself.
Mm.
What's the practical difference between A and RRT that an aspiring autonomous engineer needs to know from the BSR syllabus?
Great question. A is an algorithm that, given enough time, guarantees finding the shortest mathematically optimal path. But the downside is it can be computationally slow, especially if the environment map is large or complex.
Okay, optimal but potentially slow. What about RRT?
RRT is different. It basically sacrifices guaranteed optimality for speed. It's an algorithm designed to quickly explore unknown or complex environments by randomly growing a tree of possible paths. It finds a viable path, usually not the absolute shortest, very, very quickly. So in real-time situations like autonomous exploration or emergency collision avoidance, that quick, good enough path found by RRT is often much more valuable than waiting for the slow, perfect path from A. Mastering that trade-off between optimality and speed is crucial for real-time robotic decision-making.
So even the prerequisite test, the BSR, ensures the candidate understands the operational reality of autonomous systems, not just abstract theory.
Precisely. And the BAR explicitly includes modules that bridge these physical robotics concepts with the software and cloud side. It covers AI integration, specifically mentioning things like reinforcement learning for robotics, how the machine learns optimal behaviors through trial and error in its environment.
Learning by doing.
Right. And it covers the fundamental software framework used in robotics, ROS, the robot operating system.
And tying it all the way back to Module N6, the cloud deployment aspect.
The BASR syllabus also explicitly includes cloud-based robotics. It focuses on how to manage the data generated by these physical devices using IoT principles, edge computing concepts, and cloud deployment strategies specifically for autonomy. So mastering BASR ensures the candidate is truly ready for the MTSE program, which, as we've said, seamlessly marries that physical autonomous systems, engineering the mechanics, the sensors, the control with the scalable cloud solutions, the intelligence, the data processing, the infrastructure. It connects both worlds from the start.
Okay, we've covered the immense technical depth, the high-value career paths mapped out by the MTSE. Now we really have to address the practical logistics.
Yeah.
How does someone actually get into this program, and what's the cost structure like? Let's review those admission logistics first.
Right. The eligibility standards seem designed to filter for both talent and commitment. They give priority to candidates who have a strong academic background already. So, a bachelor's degree in fields like computer science, IT, mathematics, statistics, or economics. That provides a pretty clear pathway for people coming from a traditional university background.
But the program is also designed to be genuinely meritocratic, right? Not strictly limited by formal credentials.
Absolutely. The program is explicitly stated as being open to all, so candidates without formal degrees in those specific areas are still accepted if they can demonstrate strong foundational knowledge in programming and math.
How do they demonstrate that?
Well, that knowledge could be self-taught or maybe gained through other certifications. The key emphasis is that performance and demonstrable mastery trump paper qualifications. The only hard administrative requirement seems to be proficiency in academic English, which makes sense. It's essential for mastering the advanced technical documentation and course materials.
And the initial costs seem remarkably low,
Yeah.
especially when you consider the advanced nature of the content and the kind of salary outcomes we were just discussing.
Yeah, the entry cost really looks designed to remove that initial financial barrier, just to let you test your knowledge and see if you qualify. There's a one-time registration fee of $70. That's mandatory for everyone. And the eligibility test itself, that rigorous BASR exam covering robotics and systems basics we just detailed, has just a nominal one-time fee of $5.
$5.
$5. So yeah, $75 total to officially apply and test your way into a program that could potentially lead to a $200,000 career path. It's quite something.
And this leads us directly to what you called the real aha moment for the listener, the merit-based tuition system.
Yeah.
You mentioned the standard non-discounted cost for the 24-month program is around $35 per month, totaling about $915 over 2 years. But that's essentially the maximum price, not the typical one.
Exactly. That $915 is the price floor, or rather the ceiling. This system is genuinely unique, and it strongly reinforces MVIT's stated mission to democratize access to elite tech education by making it purely meritocratic. The actual tuition you pay is heavily discounted based entirely on your score in that prerequisite exam, the BASR.
Okay, spell this out. If you score high enough on the entrance exam, you just don't pay the monthly tuition.
Precisely. If a candidate scores 90% or above on that BASR entrance exam, proving they already possess strong foundational autonomous systems and cloud knowledge before starting, they receive a 100% monthly fee waiver.
100%.
100%. Their effective monthly tuition fee drops to $0. They only pay that initial $70 registration fee we mentioned. That's it.
Wait, just to be crystal clear, you're telling us that a candidate can potentially obtain this comprehensive 2-year industry-leading certification covering deep learning, full-stack dev, robotics, kinematics, cloud architecture, everything we've discussed for a total cost of $70, provided they can prove mastery on the entry test.
That is exactly what the source material lays out. And the discounts are tiered to reward various levels of high achievement, too. It's not all or nothing.
Okay, like what?
Scoring between 80% and 89% on the BASR yields a 75% waiver, dropping the monthly fee to just $8.75. Even scoring 70% to 79% nets you a 50% waiver, making the monthly fee only $17.50.
Wow.
Yeah. The system clearly rewards talent upfront and makes the financial barrier almost negligible for high achievers who've already put in the work to build that foundational knowledge.
Why? I mean, why would MVIT, an organization that also sells enterprise software solutions, structure their tuition like this? Potentially giving away this incredibly valuable education, essentially for free. What's the catch?
That's the strategic implication, isn't it? The sources suggest this structure serves two main purposes. First, yes, it absolutely democratizes access based on skill, not wealth. But second, and perhaps more importantly from MVIT's perspective, it acts as the most rigorous filtering mechanism imaginable.
Oh, so.
They're clearly not interested in maximizing tuition fees per student. They seem interested in filtering for the absolute elite talent people they might eventually want to hire themselves, or who will go on to drive industry success and thus elevate the institute's reputation and the value of the certification. It ensures every single graduate who comes out the other end is likely high-performing, structured, and deeply committed. It selects for excellence.
And that commitment doesn't just stop once you get that good score on the entrance exam, right?
Yeah.
You have to maintain excellence throughout the program to keep the financial benefit.
Exactly. That's the structured commitment component they talk about. Those significant tuition discounts are contingent on the candidate maintaining a 75% or higher grade in their monthly assessments throughout the entire 24-month program.
So it filters out people who aren't serious or can't keep up.
Right. It filters for serious candidates who are committed to continuous learning and high performance. If your performance drops below that 75% threshold in a given month, your monthly fee increases for the next period. It keeps the pressure on.
And there's even another tier of merit reward during the course itself.
Yes. Scoring 90% or above in any semester exam results in a full fee waiver for the entire next semester. So there's this constant incentive to strive for the highest level of mastery. This constant pressure for high performance ensures that the graduates leaving the MSIA program are truly elite and fully prepared for those demanding MLOps, AI architect, and deep learning research roles we discussed earlier. They've proven their ability to perform under pressure consistently.
This whole structure feels highly strategic. I mean, mastering autonomous systems engineering clearly requires structured commitment and sustained excellence. By setting incredibly high standards up front with the BASR and then removing the financial barrier for those who meet them, the program effectively filters for the exact type of talent-focused, high-performing, intrinsically motivated, and committed that industries desperately need to design, deploy, and ethically manage these increasingly complex, self-governing systems.
It aligns incentives perfectly, doesn't it? Rewarding the skill and commitment needed for the field itself. Hashtag outro.
So we have taken a pretty deep dive today into the Manchu Certified Autonomous Systems and Cloud Engineer certification, really distilling that MVIT roadmap. The value proposition seems incredibly clear. The MTSE presents itself as a complete 24-month system. It integrates the immediate practical functionality of full-stack development with the strategic power of advanced AI and deep learning, and then adds the necessary global scalability provided by robust cloud expertise. And it's all geared towards building and managing intelligent, autonomous agents in complex robotic systems.
Yeah, we charted those pathways pretty clearly, I think. From the M1 full-stack engineer who builds that secure monitoring dashboard, through the M3 machine learning systems engineer who manages the crucial MLOps for reliability, all the way up to the M5 AI solutions architect who commands top dollar designing those huge enterprise systems,
Right.
and the M6 cloud AI infrastructure engineer who figures out how to scale these platforms globally across AWS, Azure, GCP. It really looks like a direct merit-based map to some of the highest demand, most impactful jobs in technology today.
And as we close out, the source material did touch on that fundamental discussion that really underlies all this powerful technology. The question of machine autonomy versus human oversight. It noted that the optimal approach, at least for now, seems to involve combining machine efficiency.
Yeah.
Their ability to handle massive data processing, repetitive tasks, lightning fast calculations, combining that with human creativity, intuition, and critical thinking.
And the sources really emphasize that point. As these MPCE professionals go out and design and deploy these highly autonomous systems, the critical thinking that's encouraged by the rigorous program structure itself becomes absolutely essential for ensuring adaptable and, importantly, ethical AI.
So the machine handles the speed and the data crunching.
Right, the operational efficiency. But the certified human engineer provides the moral compass, the strategic direction, and often that necessary nonlinear common sense oversight needed when complex, unforeseen circumstances inevitably arise. Things the machine wasn't explicitly trained on.
Okay, so the question we want to leave you, the listener, with today, building on that necessity for human critical oversight, is this. How does becoming a certified expert in designing and deploying these autonomous systems fundamentally redefine the balance, maybe even the partnership between human oversight and machine autonomy in the key industries of tomorrow? Where does that line get drawn and who gets to draw it? Something to think about.